So, fun fact about the history of math. The way we know climate change is happening is based off of the greenhouse effect, right? That was discovered 250 years ago by a mathematician by the name of Joseph Fourier. Just a fun math fact. But having said that, and before we get into all of this stuff today, section 1.5, I want to let y'all know for office hours, you can either meet with me over Zoom, or my office is literally like the very back corner, straight back behind here. So you can meet with me in person or over Zoom. Having said that, let's talk about section 1.5. Section 1.5 is all about what's called the limit. Any clue what the limit might be? If y'all had to guess. Awesome, quiet stoicism for the win. Yeah, so the limit is this idea of not what your equation is equal to at a particular value, but as you get close to it, as you get close to, in this case, 1, what does your function look like it's going to be equal to? So, having said that, one way for us to find a limit is to take a table of values and evaluate our function at a bunch of different x values close to 1. And what I mean is something like this. So in this case, we've got this function x squared plus 1. And we want to know what the limit as x approaches 1 is for this function. One way we can find the answer is numerically or tabularly. By setting up this table and saying, all right, let's get really close to 1. What does it look like our function is going to get close to? Well, if you look at it from the left and from the right, so coming in from the left and coming in from the right, our function gets really close to 2. And in this case, we would say, because it agrees from the left and it agrees from the right, that our function is equal to 2 under the limit as x approaches 1. So what does this all mean? Like, if you had to tell me what you just understood me to say, what would you tell me? Quiet stoicism for the win again. I'm loving it. Man, y'all are awesome this afternoon class. Quiet, man. All right, anyhow. What it means is it's this idea of not what your function is literally at 1, but in this bubble of numbers around 1, what does it look like your function's equal to? Does that make sense what I mean? Kind of sort of yeah? Kind of sort of no? All right. So another way of thinking about this is graphically. What is our function getting close to as we approach x is equal to 1? So comparing these two methods, the tabular numerical method, and this graphical method, they're kind of saying the same thing, right? What we're getting at is, as we move from the right towards x is equal to 1, and as we move from the left towards x is equal to 1, our function gets closer to 2, right? Similarly, as we move from the left, as we move from the right. So this idea of the limit, like I said, it's not literally saying what is your function at 1. It's saying what is it around 1. Make sense? Having said that, let's consider the limit as x approaches 1 of these 3 different functions. If you had a guess, what would the limit be for A? It's hard to look at it and tell right away, right? Well, it might help to know that the graph for A looks about like this. looking at this graph, what would you say the answer was?
It's either 1 or 2.
It's going to be 2 in this case. And the reason why is, again, yeah, our function doesn't actually have a value at 1, right? Because, well, if we put 1 into the denominator, we get out 0, right? And 0 in the denominator, can't do it unless you're Chuck Norris. Dude, come on, that was killing me. Like, I'm actually funny. Anyhow. But looking at this, we could go ahead and try to graph it. When we do, it gives us a better idea. Like, okay, looking at this graph, when we're at 1, everything else looks linear, except we're at this point, right? That point happens to be at 2. Similarly, looking at B, computer's over here. Looking at B, our graph would look something like this. Notice coming at it from the right, our limit would be 1. Coming at it from the left, the limit would be -1. So we don't agree coming from the 2 different directions. And because we don't agree coming from these 2 different directions, if we were to give this a value, we would have to pick something between 1 and -1, right? There's an infinite number of numbers in there. How are you going to pick? You're not. You're just going to say it doesn't exist. Because they don't agree coming from the 2 different directions. Now, in this case, C, let me go back to it. C is this piecewise equation, right? So it's going to be equal to x everywhere our function is, except at 1. When x is equal to 1, our function is going to be 0. What this looks like is this. So line x equal to y, with a hole at 1, 1, and a point at 1, 0. So our function has a value here at x equal to 1, right? But our limit is going to be 1. So what does this tell us? This tells us that our limit doesn't depend on the value of our function at a point. It depends on the value of our function around that point. Does that make sense? Yeah? Go. Having said that, another way of looking at it, again, that numerical method, our y values get close to 1 here. Yeah? So, the takeaway from all of this. The point of this is to say that if the limit of our function approaches L, as x gets close to C, whatever C is, if that's the case, what that means is our function just gets arbitrarily close to L as we get arbitrarily close to C. Similarly, if our limit doesn't exist, or if our limit from both directions don't agree, then our limit doesn't exist. And if our function is equal to a particular value, right? So f at C is equal to something, that doesn't necessarily mean our limit will be equal to that something. Does that make sense what I mean? So having said that, the definition of a function, of the limit of a function is just as follows. And the way we read this is we say the limit of f of x as x approaches c is equal to L. You could read it a couple of other different ways, but generally said. Now, it might be useful to know a couple properties about limits. The limit of a constant is just going to be that constant, right? Because if we have a function that's just equal to a constant, it doesn't matter what x is. It's always going to be that constant. So we're always going to get arbitrarily close to that same number, right? The limit of x, of just the function x, I should say just the function f of x equal to x. As x approaches c, well, it's just going to be c. Nothing fancy about that. Similarly, we have these power rules. Now notice there's an amendment on the fourth property with roots. And that's just because of the behavior of roots, right? Make sense what I mean? All right, so now it might be useful to know how functions, or I mean, how limits are going to behave under different operations, right? They really don't change a whole hell of a lot. I mean, they do change things, but not as much as you might expect. So let's say we have these two functions, f of x, g of x. And as x approaches c, f approaches L, and g approaches k. Well, under this condition, under these conditions, if we multiply our function f of x by a constant, our answer under the limit is just going to be that constant times L. If we add two functions together, it's just going to be L plus or minus k. Product, quotient, and then the power radical. Nothing too fancy is happening here yet. Having said that, just as an example of what this addition and subtraction rule looks like, let's say we're given a function x squared plus 2x minus 3. Notice when we wanted to apply the limit, we would pull everything out of the parentheses and apply the limit to each term. And evaluate them independent of each other. And then just do the operation that links them. Having said that, there is this theorem called replacement theorem, and all it's getting at is if these two functions are equal everywhere except at one point, and that one point happens to be where you're taking your limit of, go ahead and check them against each other, right? So what I mean by that, so let's look at this example. What's the limit as x approaches 1 here? Any clues? It's not obvious, right? But what happens when we simplify it? Can we simplify it? Why don't we all try that really quick? Try to simplify this and see what happens. We'll do that. I'm gonna fill this up really quick. So who thinks they've figured it out? Who thinks they've got it simplified? It's a pain in the ass, right? Like this is a beast to simplify, isn't it? The reason why I wanted to have y'all go ahead and try to simplify it, to act as a sort of reminder that there are, I do have my algebra review notes online, and there are going to be factoring techniques that you're going to want to review as you move through these limits. Oh, the tablet fell. Awesome. All right. Yeah. So like I was saying, there are going to be factoring techniques that you want to, you're going to want to review as you go through these limits. In this particular case, long division would be your best friend. And I say that because let's look at just the graph of it, right? We can already see we're going to get a parabola. Agreed? Which means we're going to get a polynomial of the second degree. Which means that when we simplify it, we should expect something that looks like that, right? So long division would be a natural first go-to. Applying it, we get that this simplifies out to be x squared plus x plus 1. But we have this condition on it, right? X isn't equal to 1. Why not? Why do we have this condition here? Anybody know? Yeah, that's literally exactly why. Is what we're saying with this condition is, yeah, these two things are equal everywhere except at this point. Make sense? So when we apply this technique, when we simplify everything out, we get this final polynomial down here. And we can apply the limit directly onto it and get a nice easy answer, right? Agreed? So let's do that. Notice, before we do that though, this g of x, that hole was filled, right? And the reason why we want to notice this is because this is generally going to be the technique that we're going to use in this class to solve limits. We're going to try to fill the holes in different functions. In this case, it was through factoring and then simplifying. Once we do that, using those properties, well, this I can just plug 1 into according to those properties. This I can just plug 1 into according to those properties. This, well, it's just going to be 1. It's constant. So we're going to get 1 plus 1 plus 1, which is 3. Does this make sense what I mean? Yeah? Cool. Having said that, another similar problem, right? This one might be more obvious for how to factor out. When we factor this out, let me go back to this. When we factor this out, what we're going to get, it's going to look something like this. The limit as x approaches -3, x plus 3 over x squared plus x minus 6. Factoring out this numerator, it's going to come out to look something like x plus 3 times x minus 2 over x plus 3. I'm going to put the limit out front. So naturally we can factor and we can simplify this, right? When we do, we're going to get the limit as x approaches -3 of x minus 3. Well, hey, the limit of x as x approaches some constant or some value c, it's just going to come out to be c. So in this case, x is going to be -3, right? So this should come out to be -6 in the end. Agreed? So let's check it out. My mistake, I had a typo up here. It's supposed to be -2. So x would be -5. I mean, our limit would come out to be -5. Which is what this tells us, agreed? Like just looking at where this hole is, this hole's got to be at -3, -5. Well, as x approaches -3, we get -5. Filling in that hole, right? So looking at how the book goes about solving this problem, same idea. They start by saying, hey, let's apply the limit to the numerator and the denominator. Well, shit, we get 0 over 0. Okay, let's not do that then. I'll bleep that out later. So instead, let's factor our numerator, divide out those like factors, simplify the whole thing, and then apply the limit. Now, why is this? Why does this work? Any thoughts? Any ideas why all of this works? What are we doing here? Well, what we're doing, we're applying the replacement theorem. We're saying, hey, this x squared plus x minus 6 divided by x plus 3 is identical to x minus 2 everywhere except for when x is equal to -3. So, because of this, the limit should be the same. Does this make sense to everyone? Yeah? So what does this tell us about the limit? What is the limit? In your own words, somebody, what's the limit? What do y'all think? An excuse for me to yell at y'all and just talk to y'all all afternoon, right? What do you think the limit means? The limit, all it's doing is something that looks like this. Not me erasing the board, but what I'm about to draw. Call this A, they call this B. It's saying, hey, let's take these two open intervals, A to C and C to D. So we can get as close as possible to A without including A. And we can get as close as possible to C without including C. And we can get as close as possible to B without including B. So these are going to be intervals and numbers. And it says, what happens when we shrink the size of these intervals? What happens when we let A and B get close to C? Well, when that happens, let's see what happens to our graph. Well, our graph gets closer to that point in question, right? We're going to move along our graph as we approach this point. And as we do, we're going to say, hey, this y value and this y value up here, they get closer and closer and closer to L. So because they get closer to L, our function, as x approaches C, it must get close to L. That's all we're doing. The mathematicians write this as a proof. We actually say it backwards. We say that as y gets close to L, x gets close to C. But for what we're doing, what we're talking about, we can think of it in the reverse order. Does this make sense? Can I help visualize it a little bit? It's weird, right? Because what this is demanding of us to do is to think of numbers in math as something that can move, something in motion. And that's not natural to anyone. But that's what calculus is. And that's what we're going to be talking about all semester, is math in motion. We're going to be taking these sets and making them grow and shrink and getting different values out of them. In this particular case, what we're doing is we're saying, as we get close to x, our function gets close to L. Make sense? Now, what about this case? We know we need to simplify it, right? Like looking at this, probably a good idea is to go ahead and simplify. Agreed? If for no other reason, then your denominator can't be 0. So let's simplify it. How are we going to do that though? Any thoughts? Anyone have any ideas on how we're going to simplify this? What happens if we multiply our numerator and our denominator by 1? Nothing, right? What if we choose to represent 1, though, as the square root of x plus 1 plus 1 over the square root of x plus 1 plus 1? What happens then? Well, let's look. This is just 1, right? We've not done anything special here. You just represented it using the kind of the opposite idea of what our numerator is, right? We've said, let's call this thing A, let's call this thing B. So we have A minus B. So let's multiply this fraction by 1, where 1 is equal to A plus B divided by A plus B. Does this make sense? Not really, right? Like, what the hell am I talking about? What I'm saying is we can think of the square root of x plus 1 minus 1. You can think of it as A plus B. I mean, my mistake, A minus B. And if we wanted to kind of start working with this, a natural first step might be to say, all right, we've got A minus B over X. Let's multiply this by A plus B over A plus B. What this is going to give us is A squared minus B squared over A, my mistake, over X times A plus B. Well, what's the square of the square root of anything? It's just that anything, right? Like if I took the square root of something and then told you to square that answer, it would just be that something, right? So what we're going to get here is just X plus 1, that A, right? That new first value, minus 1. Well, those ones are going to cancel each other. And then you're going to be able to divide out the X that's in your denominator. And when you do that, now you've got something you can apply the limit to. Now that you have something you can apply the limit to, you can find an answer. Because these two things are going to be equal everywhere, except for when X is equal to 0. I meant to drop that. Does this make sense? Yeah. Awesome. So I've alluded to it a couple of times. There's what's called the one-sided limit. So far, we've talked about the limit, but we can break it up into two different parts. The one-sided parts. The part that comes from the left and the part that comes from the right. However, to write these, to represent these, we change our notation a little bit. To the right of C, we'll write a negative sign if we're coming from the left. And we'll write a positive sign if we're coming from the right. I don't have a mnemonic for how to remember that, quite honestly. Unfortunately, that's just one of those things you're going to have to memorize. It's always good to be right, so it's a positive thing, I guess. I don't have a mnemonic for this. But what it means is exactly what I've alluded to before. We come at it from the right, that's this case, coming in from the left. So let's look at one of these earlier problems. There we go. Here, the limit doesn't exist, but our single-sided limits do. Coming at it from the left, we get -1. Coming at it from the right, we're going to get 1. So just because your limit doesn't exist doesn't mean your single-sided limits won't exist. Does this make sense? So the way we will write this would be something like this. The limit as x approaches 1 from the left of x minus 1 over x minus 1 is equal to -1. And the limit as x approaches 1 from the right of x minus 1 over x minus 1, that's equal to 1. And the limit as x approaches 1 of x minus 1 over, my mistake, the absolute value of x minus 1 over x minus 1 does not exist. And the reason why is because the first two limits don't agree. Coming at it from the left, we're going to get close to 1. Coming at it from the right, my mistake, -1. Coming at it from the right, I get close to 1. But because they don't agree, like I said, the limit does not exist. As another example of this, you've got the absolute value of 2x divided by x. What do y'all think these limits are going to be as x approaches 0? Take a wild guess, anybody? The limit doesn't exist. Absolutely. What about the left-handed limit? Coming at it from the left. Well, if we look at this 2x thing, right? This is going to be equal to the absolute value of 2x. It's going to be equal to 2 times the absolute value of x, right? And the absolute value of x over x is going to give you one of two answers, either 1 or -1. That's why this worked the way it did. So knowing that, what do you think the limit's going to be now?
-2.
Yes, -2 or 2. Coming at it from the left, coming at it from the right. Does this make sense? Yep. -2 and 2. So we're literally just saying, what is our function getting close to? What is it approaching? Literally, what is it approaching? Not what is it approaching? What time does this class end? 6:50? Holy shit, I'm gonna get through all of this today? Yes! All right, so as we've said, we say the limit exists if both directions agree. I'm stressing this point because it says a lot about what the limit means. It's telling us that the limit, it'll be easier if I draw this. Actually, I'm gonna draw it here. What it's telling us is that there are 3 different cases we might have for our function. Everybody at home, can you see all 3 parts of the board?
Yes, I can.
Awesome. All right, so the first case we might have, it's going to look something like this. Second case, it's going to look something like this. The third case might look something like that. In this case, our limit's just going to fill this hole. So what I mean to say X is equal to C, Y is equal to L, Y is equal to L. C. That's it. F of C is equal to, let's just say some value. And that's it. All right. So what this is telling us is that here, the limit's going to give us L back, right? So it doesn't care what your function is. It cares what's close to that value, right? As you get close to C, it cares what your function gets close to. Over here, same exact story. As X gets close to C, your your limit is gonna come back as L, right? So let me write all of this out. some details into this. Let's call this lowercase m. Let's call that uppercase m. All right, so come back to this picture. What this picture over here is telling us is that as x gets close to c, our function is going to kind of bounce around some values close to L, right? Over here, this is telling us, all right, our function at c is equal to k. But as we get close to c, our function value bounces around something close to L. And then finally over here, as we get close to c from the left, our function value gets close to lowercase m. But as we get close to it from the right, it gets close to capital M. Now, lowercase m and capital M are nowhere near each other in the sense of numbers. So because they're not even close, we say the limit doesn't exist. Does this make sense? So in order for our limit to exist, the left and the right have to exist. Having said that, let's get back into these notes. You know, I thought wearing a hoodie would be a good idea today because, you know, it's cold out. Wasn't. It is way too hot to lecture in a hoodie. Awesome. All right. So in order, like I said, for this limit to exist, we can't be looking at a case like this. If we're looking at a case like this, you automatically know your limit doesn't exist, assuming that that jump discontinuity exists where C is. So what we're looking at here is what's called a jump discontinuity. And when you're taking the limit as x approaches c, then we would say it doesn't exist. But if we were to take it a little bit before, x equal to a, a little bit after, x equal to b, those limits would exist, just not at c. Does this make sense? Yep. Dope. Awesome. So, why don't y'all give this one a shot really quick? Try this example on your own for a second. So this is what the graph looks like. Looking at this graph, what do you think the limit's going to be? I should have looked closer. The limit's going to be 3. And the reason why it's 3 is because as we move towards 1 from the right, we approach 3. And as we move towards 1 from the left, we get close to 3. Does that make sense what I mean? Yes, ma'am.
Am I just confused because I don't know the properties? I'm really confused on how, like, you're solving it.
So this is right now just from looking at it, the solving part is where I was actually going to go to next.
Okay, so I just have to graph it to know.
Not necessarily. The graphing process is just a good first place to start.
Yeah.
Like it gives you a good heady way of looking at it and being like, okay, what do I think is going to happen? It's a good way of verifying what happens next, which is the map. Looking at it, coming from the left, the properties of the limit tells us that limit of a constant, it's constant, it's going to be 4. The limit of x, well, that's just going to be c. So we're going to get 4 minus 1 is equal to 3, coming at it from the left. Do the same thing. Now, why do we break it up? We broke it up for 2 different reasons. One, it's as x approaches 1, and we have 2 different functions happening when x is greater than 1 and when x is less than 1. And because our graph told us it was a good idea. So looking at it, from the left, from the right, they're equal to each other. So the limit must be 3. Does that answer your question?
Mhm.
That's right. I think we got another 2 examples. Yeah. Okay. So I'm going to say this apparently, hence this example. This example is what's called a stepwise function. And it's going to look like steps. When we graph this, it's going to look like that. So, looking at this, what we want to find is the limit as f of x approaches 2. We want to show that it doesn't exist. Why doesn't it exist? Well, as f of x approaches 2 from the left, we're going to get close to 14, right? We're coming at it from the right, we're going to get close to 16. So since they're not equal, the limit doesn't exist. Everybody cool with this? What about this problem? Is it possible?
When you have 0 in the denominator,
Yeah, we get 0 in the denominator. There's not a clear-fire way of clearing that up, is there? So what do we think? Well, what happens as we get close to 2? Our function coming from the left, it's going to get close to negative infinity. And coming at it from the right, it's going to get close to infinity. So to show that, our function is going to look something like this. So approaching 2 from the right, we're just gonna get really close to infinity, right? Like if we could be Chuck Norris and reach infinity, we would reach it. And coming at it from the left, it's gonna be negative infinity. We don't agree. So we would say that the limit does not exist. Welcome to the world of infinity. This is where a lot of our problems, I shouldn't say a lot, some of our problems are gonna sit. We're gonna start getting limits that can have infinities in. All infinity really tells us is that if you pick a number, there's gonna be a number bigger. Pick a number, there's gonna be another one bigger, so forth, so on, or smaller. That's all this infinity is really telling us. But because they don't equal the 2 limits from the left and the right, we say it doesn't exist. Now check out this notation. This notation tells us f of x approaches negative infinity as x approaches 2 from the left. That's what that arrow means, approaches. Having said all of this, some basics. I want y'all to go back home and look at this slide tonight. This slide is just a good way of checking to see what you do and don't understand. It's a good preparatory question type thing. Since the exam's going to be next Thursday, this would be a good place to start. Having said that, I already told y'all that I posted study guides. No, awesome. All right, so for those of y'all at home and everybody here in class, there are 2 study guides posted, one on Webaside. It's not for our grade, it's just study guide. And another one on Blackboard. Again, not for our grade, just as a study guide. The first exam will be next Thursday. It will be on Webaside. We will not meet. Also, before I forget, there's a question of the week this week. So, good idea to check it out, everybody. It will be open until Saturday night. Having said that, let's move to section 1.6. Before we get there, non-rhetorical question. This graph, we just said that the limit doesn't exist because the limit from the left and the limit from the right aren't equal. What are we describing when we say something like that? Describe this picture. What does it look like to you? I didn't.
Distance between the 2.
Yeah. Another way we could say that is this graph, it's not continuous, right? It's not connected. There's a break in it. That is what we're going to be talking about now. The idea of continuity and what continuity actually means. We have to meet all 3 conditions. All 3. Yeah, that's a pain in the ass, right? Because that means you've got 3 things to check here. The first thing is to see that your function's even defined at C. The second thing if the limit of your function exists. And the third thing, if what your function is at C is equal to your limit. Well, in this case, we failed, right? Our function doesn't have a limit. And if we think back to those earlier graphs, I went way too far back. If we think back to this, our limit exists, but our function doesn't have a value there. Here, our limit doesn't exist, and our function doesn't have a value. Here, our limit exists, our function has a value, and it's equal to what our limit is. And finally, the coup d'etat. Function has a value, our limit has a value, but they're not equal. So continuity is quite literally saying your graph is continuous. There's no break in it. Make sense what I mean? Yeah? Cool. Having said that, where the hell is this slide now? There it is. So these three conditions combined, they literally mean that your function isn't broken at C, that it's all one piece. Is everybody cool with that? And in that way, we can think of it just like that. You can draw your function without lifting up your pencil or pen. All right, so when a function is not continuous, we say that it's not continuous at points. And the reason for that is because it's discontinuous at points. It's not likely to be discontinuous everywhere, just at points. Does that make sense? In this particular case, here, here, and here, right? But it's continuous everywhere else. So to talk about a function as being discontinuous is to talk about it at points, not on intervals. To talk about it being continuous is to talk about it on intervals, not on points. We say that a function is continuous between C3 and B, between C2, C3. And we say that it's discontinuous at C1, at C2, at C3. Make sense? So, where a function is continuous, well, it depends on the type of function. Polynomials, everywhere. Rational functions, they're only continuous in their domain. 2 is not in the domain. This is not a rational, or this is not a polynomial, it's a rational function, right? That's what we're saying here. Having said that, I think I'm going to go over this example and then let y'all go. Looking at just these two functions, really quick, where do you think they're continuous and discontinuous at? Well, they're polynomials, right? And that last rule, they're continuous everywhere. So these two functions would be continuous everywhere. As evidence of that, there's no breaks in them, right? Having said that, I will let y'all go, just because 7 minutes isn't enough to go through anything else, really. We'll stick around if anybody else has questions.